So this becomes volume equals 2 pi integral from 0 to 2 of x cubed dx, which is 2 pi x to the 4th over 4 from 0 to 2. 2 pi times 16 divided by 4 is 4. So that's 8 pi units cubed. That's the easy part. Right, the hard part on these is to set them up. Okay, just for fun, let's go ahead and do this as a washer problem. All right? And hopefully we get 8 pi units cubed. Right? That's the idea. But when we do it as a washer problem, lots of things are going to change. So I'm going to draw our washers. So given a random cross section, right? So we have these washers stacked on top of each other. You see that? It's kind of cluttered, I know. All right, so these washers are on top of each other. The formula for this volume with the washer method is going to be the integral. Now, will this integral be a dx or dy integral? Dy, because they're sliding along the y-axis. The thickness of each of these washers is dy. So that's a dy integral. And along the y-axis, it starts at 0 and slides up to what number? What, Ryan? 4, right. 0 to 4, right? Because when x is 2, 2 squared is 4. And then it's going to be pi times big R squared minus little r squared. That's the formula for washers, because you're taking the area of the big circle, cutting out the circle on the inside. Okay, so this is going to be pi, integral from 0 to 4. What's the radius of our big circle here?
2.
The radius always? Yeah. You're right. It is always 2. Right? This is a vertical line. So no matter where our washer is, we're only cutting stuff out on the inside. We're not cutting it out on the outside. And then it goes straight up. So that's just going to be 2 squared minus little r. Well, earlier we said little r was x. Question? What do you got? What do you think? Well, it's a dy integral. So this r is x. So how can we write x in terms of y? Square root of y. Everyone understand why it's the square root of y? This distance here is x. Right? And we know that y equals x squared. So solve for x. You get the square root of y, quantity squared, dy. Okay, so now we can solve this. This is pi, integral from 0 to 4 of 4 minus y dy, which is pi of 4y minus y squared over 2 from 0 to 4. So that's 16 minus 8. And look at that. Same answer, right? So now let's look and kind of talk about both methods, the washer method and the shell method. For all of our problems, for when you're revolving regions around an axis, you can always solve by either the shell method or the washer method, or it could be a disk method, right? Disk or washer method. You can always do it both ways, but here's the catch. Sometimes, if you pick the washer method, you'll get an integral that you can't solve, that you do not know how to do. Which tells you, now try it with the shell method, because that will give you an integral that's easier to solve, so that you can do. And vice versa. Sometimes you start trying to set up a shell, then you get your setup, but then you realize you can't integrate it. So you got to go the other way, especially with trig functions. Now, if you have a trig function, if the washer method uses the sine function, the shell method will use the inverse sine function, and you guys don't know the integrals of your inverse trig functions. Okay? So that's a problem. Okay, but you have to know how to do both. You have to know how to do both. Also, keep this in mind. The washer method, the washer integral was a dy integral. What was the shell integral? A dx. That relationship will always be the case. Okay, so that tells you if you have a hard time setting up the shell method, because it's hard to visualize, right? I know the shell method is pretty tough when you first learn it. Try to set up your washer. and figure out if you did washers, would it be a dx or a dy? And if you can visualize that, you know that the shell method will be the other way. Follow me? So like you can use that knowledge to help set up your integral. So if you know the wash will be a dy integral, then that tells you, well, if I do the shell method, it's going to be a dx integral. Okay? Alright, so let's do a problem in your book. And we did a really good one earlier today, so let's do that one again.